Good afternoon, everyone. So welcome. We have today a pleasure to have the talk by Professor Karen Yeats, who is also one of the speakers who do not need introduction. Karen studied made undergraduate degree here, I believe in Waterloo, and then the PhD thesis wrote at the University of Boston, and afterwards joined Simon Fraser University, and after several years there, joined University of Waterloo as a faculty here at the Department of Combinatorics and Optimization. Karen is a recipient of Humboldt Prize, Humboldt Fellowship, and also a double recipient of Canadian Research Chair in Combinatorics and Quantum Field Theory, I believe. Yeah, so we are looking forward.
Thank you. Okay, so I think I scared people away with my long title. It sort of looks like a 19th century cover page, right? It's like fills up multiple lines. The good news is, I guess you guys came because hopefully you think that at least sounds potentially interesting. But the other part of the good news is this is probably the last time you'll have to put up with hearing me talk about this, because the conjecture I've been trying to solve for 10 years, I managed to solve it. So near the beginning, so I was on sabbatical last year, and near the beginning of my sabbatical, I went to visit Erik Panzer in Oxford. And you know, I'd had some thoughts over the last few years, including stuff I'd done with Simone who was a master's student of mine here. And he'd had some thoughts that were in a slightly different direction. And just sitting at the board, we realized that if we put them all together, then we could prove this conjecture and a bunch of other stuff. And then it took us about 6 months to write it all up, but it's been on the archive for quite a few months now. So what I'm going to do is I'm going to spend probably more than the first half trying to convince you that maybe this is actually an exciting thing. And then I'm going to tell you a bit about how the proof worked and how it actually does more than just solve that one conjecture. So the first part is my usual story, which many of you have heard before, but you're going to hear it one more time, and hopefully I can convince you that it's interesting and exciting. And then I'll tell you the new piece of the ingredient that goes in. And I have told various parts of this to various people. So in particular, if you regularly attend the algebraic graph theory, you've actually heard most of this already. Anyway, so we're going to start by talking about Feynman periods. All right, and I think I'm going to start with the definition, and then I'm going to actually give the motivation of why this is like a thing that maybe physics would tell you is an interesting thing and not just some sort of ugly thing that I wrote down. So I want to start with, I'm going to start with, say I have a graph G. It's one of those talks. It's one of the talks where G is a graph at the start. And then I'm going to define, well, I usually call this the Kirchhoff polynomial, but you might prefer to call it the dual Kirchhoff polynomial. Or I think no one in this audience is coming at it from a physics perspective, but if they were, you might want to call it the first semantic polynomial. So what do? You take a sum over all the spanning trees. And then you take a product over, and I'm going to take the edges that are not in the tree. That's why it's the dual one. And then I'm going to make a monomial out of those edges. So I've assigned a variable to each edge of the graph. And I now take the monomial of the edges that you have to cut to get the tree T. OK, and then with that in hand, I'm going to define something else, this PG. And what's it going to be? It's going to be an integral. And you should morally think of the integral as just being this. But of course, if I write that, I'm not going to do very well in my calculus class because I've left out a lot of important things. I need to tell you what we're integrating over here. So these variables go from 0 to infinity. And I actually, well, there's a few ways you can think about this. If you have an algebraic geometry hat and you want to put it on for a moment, you can notice that this is homogeneous. I can think of this as a projective integral, and I can put a projective volume form up here. But I'm going to not do that. Let's just be super concrete, and let's just take an affine piece. So I'm going to set one of the variables to 1. Doesn't matter which one, so let's set the last one to 1. And then I just integrate over the rest of them. OK? And this this guy will, if things are nice enough, this guy will converge. And so what's the context that I care the most about and the kind of graphs that I like the most are the following. And these are, it'll converge in this case. So if G is some other graph minus a vertex where K is 4 regular and internally 6 edge connected, then this will converge. OK, and internally 6 edge connected means, look, if it's 4 regular, obviously there are 4 cuts. There's the ones that just cut off a vertex, but not those ones. There's no other ones. OK? So this is my, what I want to call the Feynman period. It's some integral. There's some polynomial here that's defined in a very combinatorial way from the graph, and I'm just integrating 1 over it. OK? So if I toss that at you with no context and no reason why you should care about it, well, probably for many people, your first response is going to be, oh, I don't like integrals. And I sympathize. But maybe your second response would be, especially if you maybe think a little bit in a algebraic geometric or more combinatorial way, is you say, OK, look, there's some integral. Maybe I don't really know a lot about it. But it's going to be controlled by this polynomial, which is very combinatorially defined polynomial. And in particular, the variety, the vanishing set on points where this polynomial vanishes, those are going to clearly be very important because they're going to give poles in this integrand here. So you shouldn't be too surprised that maybe this is an interesting thing, both just from a sort of algebraic graph theory perspective and also from an algebraic geometric perspective. And sure enough, it is. But you might also be like, OK, fine, but I could write down lots of things that would be interesting from an algebraic graph theory perspective or an algebraic geometry perspective. Well, why this one? And the answer to that is the physics. So where does this come from? I realize that I do tell this story a lot because it's part of the standard sort of underlying story of a lot of research that I do. And I usually sort of just, well, I always wave my hands, and I'm going to wave my hands today. But, and I literally do because that's the way I speak. But in particular, I usually actually don't really even show you the sort of sketch of how you get this out of the Feynman integral. And so I thought today, since maybe this is the last time I'm going to tell a big part of this story, I thought I'm actually going to sketch out how you get this from a Feynman integral. And you'll see that as long as you squint enough to not get annoyed at the integral signs, then it's actually, again, it's just algebraic graph theory. So where does this come from? And if you only like rigorous mathematics, you've got to ignore about 3 boards, because this is going to be the extremely sketchy part here. OK? So first of all, you have to say, well, what's the story? What's sort of the story of high energy physics? What's the sketch of high energy physics? The idea is you have some particle accelerator, and you have some particles coming in, say, and then something happens, and you don't know what. And then you have some particles coming out, and you have detectors, so you know what those are. And so you know what came in because you prepared the beams, and you know what comes out because you have detectors, and you don't know what's happening in the middle. And that's the basic story of high energy physics. And so what do? Well, you want to sum over all the possibilities for what happened in the middle. And you know, that's kind of nice. So this is a perturbative expansion. It's some expansion in some coupling parameter that's the very roughly the probability of the interaction occurring, of each interaction occurring. And so what you end up with is some sum over graphs. And each graph is contributing, well, very roughly its probability. Actually, it's amplitude, probability amplitude. And how do you write those down? Well, you can, for each graph, you write down an integral. And that's the Feynman integral. So you want to sum overall possibilities. These possibilities are graphs. They are graphs. And each contributes an integral. OK, and we're going to stick to the simplest case, which is what's known as phi4. So it's a scalar field theory. So there's a bunch of things that you don't have to worry about because they're scalars. And then what is going to happen in this simple case, in this simple scalar field theory? Well, our graphs are four regular, but they're not quite four regular in the usual graph theory sense because you're allowed to have external edges. And so, for example, I might have something like this. I've got, say I've got some particles and something like this. Let's say this guy here is, well, it's sort of like a K4, but these guys, I don't want to think of them having an extra vertex on the end. They're just coming from, they're freely propagating out way out there, and I only start thinking about them once they're close to my graph. Okay, so that's a graph with an external edge, with four external edges. And now what do I do with this? Well, for my graph G, so take such a G, and here comes the super sketchy part. I'm going to write down an integral, and here's what it's going to look like. I want to imagine that I'm summing or integrating over all of the possibilities that would have this graph shape. And so I'm going to do it in what's known as momentum space. So what I'm integrating over is all the possible values of the momenta of these internal edges. So I'm going to have a product over the edges of the graph, which I mean the internal edges, not these little external guys. And for each one of those, there's some momentum, which I'm going to call P sub E. And it'll be a 4 vector because we're here in the real world, and we got 3 dimensions of space and 1 dimension of time. It's an energy momentum. Okay, and I'm going to, no, that's not what I want to write now. This is where I want to put the derivative. So I'm going to write d4, not the derivative, the differential. So this is where I'm going to write d4 to remind us that we're in 4 dimensions. Okay, what else do I know? Well, I know there's momentum conservation at every vertex, because that's how particle interactions work. So I'm going to take a product over the vertices of the graph, and I'm going to put a delta function that's going to force all the edges, the sum of the edges incident to that vertex to be 0. And I put a plus or minus there because, of course, there's details. If you do it all out in detail, you're going to have to choose some arbitrary orientation, and then that is the direction of your momentum. And so this is really a signed sum, but that's fine, whatever. There's some other details as well, but which is that I also would really like some momenta for these, some external momenta. So when I get to these vertices here, then when I said E incident to V, I really want to include actually the external guys here, but here I don't. Well, that's fine. And then what does each edge contribute? It contributes what's known as its propagator. And what does that look like? Well, I want to sort of morally think of it as PE squared, and if we were in the massless case, it would be exactly that, but you might have a mass, something like that. My story like that, okay? And that's just sort of what physics tells you that propagator is supposed to contribute. That's just what it tells you. Okay, so now I want to simplify this a little bit, because if you have this kind of a constraint, sometimes in a context that isn't coming from quantum field theory, instead of thinking of it as momentum conservation, you might think of it as a harmonic constraint. Right, because you're saying around each vertex it sums to 0. Okay, well, if that happens, you say, well, you know, I've really got too many variables here, right? Because I got all these delta functions, so clearly I could use those to get rid of a bunch of the variables. And if you think about it for a little bit, you'll see that if you do that, the number of variables you have left is exactly 1. If you take a basis of the cycle space, there's exactly 1 for each cycle of the cycle space of the graph, which kind of makes sense. So I could rewrite this integral as now I'm going to go over C in some basis of the cycle space. Okay. And then what am I going to do now? Well, I'm now going to choose 1 momenta to go around each cycle. So this is still a D4, but now let's index them by C to remind us that they come from the cycles. And then what's going to happen, that's going to eat up all of the delta functions, except there's one extra, well, you have eaten them all up, and you've also imposed then the overall momentum conservation, which clearly you want. And what's left are these guys, but now this PE is now some linear combination of the PC. In particular, it's going to be the signed sums of the cycles that are going through that edge. So we can rewrite this as follows. Now we get the E in the E edges of the graph, 1 over, and I guess, let's just say that. Oh, that's C now. Okay, and that'll be squared, and there's still going to be a minus ME squared, something like that. And notice you'll still, so I've slightly lied at this point because you also need to take care of the external momenta. They're going to still be in these delta functions, so they will still appear. You can think of that as routing the external momenta through the graph. At this level of sketch, I don't want to worry about that. Did I mention the squared is norm squared? That's something physicists do. Because they use it so much, that just keeps the notation a little bit lighter. Okay, so I just mean norm squared, nothing complicated. I mean Euclidean, if you knew what I mean by that. So it's just a completely ordinary dot product of the vector with itself. Okay, well, now I want to use something. So now, see, I said there were going to be 3 boards of just complete hand-waving nonsense. So now I want to use something that I have 1 over something, 1 over my propagator. So that's my PE squared story. Well, there's another way. I could just use the fact that I know how to integrate an exponential function to write this a different way. I could write this as e to the minus a times this propagator from 0 to infinity. OK. So if you don't like the hand-wavy part, you can just say, OK, do I remember enough calculus to do that? And now let's use that everywhere. So I'm going to use that everywhere. And what am I going to get? Well, again, so I still have this part. I still have this basis of cycles, cycle space. I still have the D4PC. I still have, well, actually, before I put that product, I think I'd like to put all the other integrals, so these ones, 0 to infinity. Because now I do have this, E in EG. But I've got 2 things going on here, because for each of these, I have this DAE, that A, 1 for each edge. And then instead of this thing, I have my exponential there. So E to the minus AE, and then this piece of garbage here. OK. So that's a thing. And you can say, OK, that's a thing, and I don't want to write it that way, because look, there's a quadratic form and then some extra guck, right? And that's how you want to think of it, quadratic form and extra stuff. OK, so how does that look? Oh, and while I'm at it, look, I'm going to switch the order of integration, because I kind of like this one better now, right? Because if I'm doing these guys, look, the main part is just going to be Gaussian. And you may say, well, I don't remember how to do a Gaussian integral, but Wikipedia does. So you can just look that one up. So I'm going to switch the order of integration. And then I'm going to have this other part. And what's this other part going to be? Well, you're still integrating over this basis of the cycle space. And, oopsie. And then what do you have in here? Well, in here you have some sort of quadratic form. So if I put all the momenta together into some vector, and I got some matrix here, and there's all the guys together. And then there's some extra craft at the end, right? So that's what's up in the exponential. Ooh, parse error. And so we just have to figure out what those matrices are. And I'm going to tell you right away that I'm not going to worry too much about this one. What's this one? Well, it's got the m's in it. It's got the external momenta in it. It's just got, I don't know, extra stuff. We're just going to stuff. Stuff involving masses and external momenta. The interesting one is this one. And this is where I said secretly this is just all algebraic graph theory, right? I wrote a lot of integrals down, but first I just noticed that some sort of harmonic or momentum conservation property really just means, yeah, basis of cyclospace. And now I want to look at that matrix. So if I'm looking at the ijth entry of this matrix, well, what is that saying? That's saying I'm going to have a pi and a pj showing up. So that says, I need, the ijth entry is going to be where you get a pi and a pj. So coming back here, that's going to be whichever a's had the property that you're going to get a pi and a pj. Okay, but when's that going to happen? It's going to happen if there was a pi and a pj in here, so then when I square it, I'm going to get a term that has one of each. So that's going to happen when pi and pj are both cycles that go through E. Okay, so the ijth entry has an AE when cycles I and j both go through E. Hey, that sounds like the graph Laplacian, but with the cycles in place of the vertices. And if you work out all the details, that is exactly what it is. So it's a dual graph Laplacian. So this is like the graph Laplacian. Oh, that's not going to show. OK, I said the bad stuff was going to be on 3 boards, but it's unfortunately going to go on to 4, so let me just finish it up here. So this is the graph Laplacian, but cycles in place of vertices. So it's like a dual Laplacian, and that comes right back to why I like to call this just a Kirchhoff polynomial, but really it's the dual one, right? So it's the one that goes with that matrix, not the one that goes with the usual Laplacian. And it's Laplacian with variables in there. I like my Laplacians to have variables in them. OK, so now you go open Wikipedia and you say, how do I do a Gaussian integral? And Wikipedia tells you 1 over the square root of the determinant of that. OK? But these are 4 vectors. So I have to take my square root determinant to the power 4. OK. So what do I get by Wikipedia, or by Gaussian integrals, really? D-A-E. There's some stuff in the numerator that I'm not going to worry about. What I'm going to worry about is the denominator, which is that. It's the determinant of that matrix, but by the matrix tree theorem, the determinant of that matrix is the Kirchhoff polynomial. So there you go. And now, OK, now I'm going to truly just hand wave the last part. If you look at this stuff a little bit, you can see that you can pull out a gamma function that has sort of the divergence in it, basically. And then if you set the momenta, the external momenta and the masses to 0, or if you just think of an expansion in them and you take the constant part, then you will get exactly that period coming out. So you pull out a gamma and sort of take the leading term, and you're going to get exactly PG. And that's classic, by the way. It's in, for instance, Zuber, which is a very, very classic quantum field theory textbook. So there. Now, if you follow those 4 boards, you've passed your quantum field theory exam now. All right? That's the only thing you need to know about quantum field theory. I was preparing this talk, and I got to the point where I said, that's classic. It's in Itzikson and Zuber. And then I realized, I don't know where my copy of Itzikson and Zuber went. I lent it to somebody before COVID, and it didn't come back. I think it's gone now. OK. If you didn't like that part, and so you went to sleep or you thought about something else, now's the time to come back. Because that's just motivation. And so if you thought it was crap, You just have to be motivated for some other reason. Okay, period symmetries. So for the rest of the talk, I just want to say, look, I like that PG. I like it because I told you I did. And from now on, we're going to think about it in terms of graph theory and maybe now and again in terms of a little bit of algebraic geometry. But we're not going to think about it in terms of physics anymore. Okay? So it's a thing. It's a thing about a graph you can write down. Okay. And so it has some nice symmetries. So I'm going to write down some of them for you. Let's start with if G is planar. We already saw there was something kind of dualish going on here, right? So it might not surprise you to learn that PG is equal to P of the planar dual of G. That's kind of nice. Oh, and by the way, I want it to always converge. So I'm always going to, if I have a graph in this location, I'm always going to assume it is one of these things that's a 4 regular graph minus a vertex, and that the 4 regular graph was internally 6 edge connected. This is an example, by the way, of such a graph, right? Because I don't need the external momenta anymore. When I did this very last step here, when I pulled out this leading term, I got rid of the external momenta. So now I'm looking at honest to goodness graphs that are 4 regular, but you take out 1 vertex. Okay? So that's nice. Incidentally, this is by Fourier transform, which I think is kind of cool, because normally you don't think of planar duality as being the Fourier transform. But if you go back to those integrals, if you liked them, for those of you who liked them, do a Fourier transform, and you'll find the planar dual just pops right out. Kind of cool. OK, what are some other symmetries? So another one, so this is duality. This is the duality symmetry. This next one is what I want to call completion. So if I have, I'm always going to use the letter G for my graph after I've removed the vertex, and I'm going to use K for my 4 regular graph. And if I remove 1 vertex or I remove a different vertex, it doesn't matter. This one's called completion. And the reason it's called completion is you actually think about that graph and think about putting an extra vertex at infinity, completing it in that sort of putting stuff at infinity sense that connects to, well, the external edges if you kept them, or just to the places where the degree is not all the way to 4. And then what this is saying is that if you actually, you can imagine rotating the graph now to put a different vertex at infinity, and that P is invariant under that rotation. And in fact, you can make that precise, and you can actually make the proof that way. OK. I'm told I shouldn't use the last board, so I'm going to come back over here. Maybe I'll just keep those a little longer, and I'll erase the hand wavy part. So what else do we have? Well, because of that, completion invariance, I don't really care which vertex I remove. So I can actually just draw K if I want. So if I have this guy, and I don't care what vertex I take away, whatever your favorite one is, then it turns out this is the same as this guy. You got to practice a while to draw that correctly. All right, so what happened? I have a graph that has this 4 vertex separation, and I can take like a Klein 4 group type action here, right? I don't get to just do any transposition, but I can do any pair like that. OK? And the period's invariant under that. And you can actually do a proof that's sort of similar to that one about rotating and putting the right vertex at infinity. OK, what else? There's a nice product property. When you saw 3 here, you might say, well, what if there's, sorry, you saw 4. What if there's 3 minus a vertex? Well, this turns out gives you a product. Okay, and so here's where the drawing gets a little tricky. The blob is just graph, right? There's just some graph in here. And if I wanted, I could just sort of shade it in lightly. Right, so there's some nice graph in there, graph in here. Okay, so here's some graph. Okay, and the reason I'm making a point about shading in this graph is I'm now going to draw some explicit edges, and I don't want you to confuse them with the blobby stuff. So I'm going to draw 3 explicit edges, that one, and that one. Oh, I didn't do a good job. There. So I put a triangle. I took the 3 vertices here, and I put a triangle there instead. And now I'm going to, guess what, do the other thing on the other side. So this is blob, 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 blob. And I'm going to do this. Okay? So this is some sort of 3 join, right? Or triangle sum of your 2 graphs. It's a perfectly sensible thing. People do that in graph theory. Oh, forgot to take out a vertex. Don't care which one. Okay? So there's a product property when you have this 3 vertex separation. And again, that's an operation like graph theorists do that. I'm not just being some complete wacko by doing that operation. There's one more that's a little bit more annoying to draw. Okay, I'm going to try to draw this one. So this one's a bit more of a pain. So first you have to get rid of the vertex. So this is now G, not K. Note, this is G, not K. And so in G I have this. Okay, that's fine. And then what am I going to do? I'm going to do something. I also need an extra hypothesis that one of the sides is planar on one side. And then what do? I get a color. And then I say, OK, look, I can take the planar dual of this side here, right? So I do a planar dual like I'm teaching a class. But I put a vertex here and a vertex here and a vertex here. So, looks like that. It's got 3 special vertices. And this one I'm going to put here. And this one I'm going to put here. And this one I'm going to put here. It's in fact the only thing you could do. It just looks a little weird when you first see it. Okay? Oh, right. You're going to look back. Someone's going to look back at the video, and they're going to be like, what the heck is that? But I'm going to leave it at that, because that's not the one I want to focus on. And it's kind of a pain to say more. But if you actually sit down, there's really only one thing I could have possibly meant, and that's the one I meant. OK. So far, I've talked about the symmetries of Feynman integrals, or at least Feynman periods. But I got a lot of words still in my title that I haven't even touched, and I'm more than halfway through. So I got to get you some more words. So I said graph invariants with the same symmetries as the Feynman integral. So I better get you some graph invariants. And what do I mean by graph invariants? I just mean like I take a graph and I get a number or a sequence or some sort of thing out of it. And so here's the one I'm going to talk the most about, because that's the C2 of the last thing here. I'm going to define C2 of G at a prime P. You can also do a prime power, but I'm just going to stick with a prime for the moment, of the graph G. And G is always the kind of graph that it was over there. What is this going to be? Well, this is where you have to put on your algebraic geometry hat for a moment. And you have to say, OK, look, I'm wearing my algebraic geometry hat. And I say, look, this is clearly controlled by the variety defined by this polynomial. And if I want to understand something about the geometry of this variety, well, maybe I could look over finite fields and learn something. If stuff is nice enough, that'll help. So that's what I'm going to do. I'm going to take this polynomial. So I'm using this notation here, like this, for the number of FP rational points on this variety. Okay, and if you don't have an algebraic geometry hat, that's fine, because this is totally, totally concrete. You have this polynomial, you plug in numbers that are 0 to p minus 1, and then you see if it's 0 mod p, right? Completely concrete. That's all I'm asking you to do. Okay? It turns out that if your graph has at least 3 vertices and is connected, oh, my graph should have been connected. Connected? Connected. I'm sorry, I'm one of those terrible people that my graphs are always connected, and so sometimes I forget about that. Anyway, if your graph is connected and has at least 3 vertices, then this turns out to always be divisible by p squared. And then I want to take that modulo p. And that's what I'm going to call C2 of G. So in general, you would get your C2 invariant would be the sequence indexed by the primes that are those numbers. Okay? Well, now I have to tell you a little bit of story about why you should care. Because, okay, I mean, I can write that down, but why do you care? So what? Okay, so this is where you just have to imagine, if you don't have an algebraic geometry hat, you have to imagine that you have one for a moment. And so it turned out, and we're also going to time travel back to the 90s to start. So we're in the 90s. Some physicists, notably Dirk Kreimer and David Broadhurst, had calculated these PGs for some graphs. Other people had too, but they did a really nice systematic study of them. Fairly systematic study of them. And what they noticed is all the ones they could compute at this point in the 90s could be expressed in terms of multiple zeta values. Multiple zeta values are some nice numbers that generalize evaluating the Riemann zeta function at a positive integer. So those are nice number theoretic numbers. You go ask the right kind of number theorist, and they'll be excited to see multiple zeta values. So that's useful when you go to the garden party over for pure math. Okay? So now you have to imagine that you have a strong algebraic geometry hat. Maybe you're even Kontsevich, say. And you say, okay, look, it looks like these are all expressible in terms of multiple zeta values. And if they're all expressible in terms of multiple zeta values, they ought to all be expressible in terms of multiple zeta values for a good mathematical reason, right? Not just because the universe is conspiring to make this happen, but for some good mathematical reason. And if you're Kontsevich, you know what that reason is. The reason why you're only seeing multiple zeta values should be because those varieties are mixed Tate motives. All right, what the heck is that? Well, it means they're especially nice, and in particular, one of the consequences of them being especially nice in that way is that the point count, just this guy, should be a polynomial in P. That's a weird property, right? You take each different prime and you do this calculation. There's no reason that the number you get out should be a polynomial in P. But if your variety was sufficiently nice, and sufficiently nice in this context means mixed Tate, then this will be a polynomial in P. And if this is a polynomial in P, well, it's also a polynomial in P that's divisible by P squared as long as the graph has at least 3 vertices. We already said that. So then this is the quadratic coefficient of the polynomial. And that's what the 2 in C2 is. It's because I have a polynomial and I expanded out and I gave names to the coefficients. And the quadratic coefficient I called C2 for obvious reasons. Okay? And that's the smallest coefficient that might be non-zero. Sometimes it's 0 too, but all the lower coefficients are always 0. So that's like an important coefficient in this polynomial. And so in particular, if this is a polynomial, then this is just a number. It's not dependent on P. Okay, so that's how the conjecture worked, and people thought about that, and Stanley did some work on that too. But it turns out it's false. So it's just false from the beginning. The periods are not all expressible as multiple zeta values. And in fact, if you'd thought about it in the 90s, you might have even been able to guess this, because there were ones they could compute and there were ones they couldn't compute. And guess what? The ones they couldn't compute turned out to not be multiple zeta. So, but thinking about it this way is still useful, because what it means is the C2 here, how far it is from being a constant, independent of P, is a measure of how far this variety is from being mixed Tate. And it's a useful measure of that. It's a measure that actually lets us conclude some things about what sort of numbers show up in that period. Are they multiple zeta? Are they a little bit worse than multiple zeta? Maybe just a little field extension away. Are they a bit worse than that, like coefficient sequences of modular forms? Or are they even worse than that, and we have absolutely no idea what they are? So you can bring the modular forms up at the Pure Math Garden Party too. Modular forms are good. People like those. Okay, but I really need to move on. So that's why. It's not written on the board, but that's fine. It also then, for obvious reasons, was conjectured to have these symmetries. Okay? So you have to listen to get C2 what, so what, but so also C2 is conjectured to have the symmetries. It should. If it's telling us what it's supposed to be telling us about the period, it really had better satisfy these symmetries the period satisfies. But it turned out to actually be pretty hard. And so that conjecture was more than 10 years old when I solved it a year ago, when Erik and I solved it a year ago. And one of the reasons I really like it, and I hope I'm starting to convince you that it's kind of exciting, is because of the way it combines the physics, the algebraic geometry, and the combinatorics. Because as soon as you start playing with this, you start to realize that you're playing with that Kirchhoff polynomial. You're just playing with graphs and these polynomials defined on them. So it really brings all of these three things together in a pretty cool way. Okay. But playing with it naively, well, it didn't end up being enough. Well, this is pretty naive in the end, but we needed a new insight. And so now I want to tell you about diagonal coefficients and the Martin recurrence. Okay. We're still in that situation over there where G is K minus phi. But now K could be 2K regular. Doesn't have to be 4 regular anymore, because this story works, this part of the story works for K larger than 2. Okay? So there's a key recurrence. I'm going to be interested in functions of a graph, and they're going to always be up at the level of K now. They're functions of a 2K regular graph that have the property that for any vertex of the graph, what I can do is I can sum over, well, I got that vertex, it's got 2K neighbors. I can sum over any matching of those 2K neighbors. And I can just replace that vertex with edges that give that matching, right? It might be a multigraph, I don't care. Multigraphs are fine. Okay, so I'm going to call that tau, and that's just a matching of the neighborhood of V. And I'm just going to write K sub tau for like you did that to the graph, and you now have a graph with one fewer vertex. Okay? So I'm going to be interested in graph invariants that have that recurrence, that satisfy that recurrence. You can think if you know any yourself that are like that. You can also, if you're not liking what I'm saying, think if you know any graph invariants that satisfy all of these symmetries. And then you can see if they do both, because that's the best part. Okay. So where did this come from? This came from Erik Panzer's Martin invariant. Okay, it's called the Martin invariant because you can get out of the Martin polynomial, but I might skip that part because I'm running out of time here. M satisfies star. That's the first one. And then you just have to tell me how I'm going to normalize it. And he's going to normalize it so that if your graph has a loop in the sense of graph theory, then it's 0. I say loop in the sense of graph theory because you've probably heard me complain about this before, but the quantum field theorists call what we would call a cycle a loop. And that's a little annoying. But you just have to put up with it. Okay, if it's just a duplicated triangle, then he normalizes that to be 1. And then you can work out using the recurrence in reverse what the multiple edge has to be. It turns out, so this is actually extra information. You don't need the last one here, but it is true. It has to be 1 over k factorial if you started with a 2k regular graph. Okay? Now, M, this M, this recursively defines some number for a graph that's 2k regular. It satisfies the symmetries. The proofs are basically all inductive, because not this one. The other ones are all inductive. You sort of do it on, well, this one's automatic. There's nothing to be done. It's on k itself. But those ones are all inductive. You do it on one side of the graph and use induction. And the base case is always small enough, you just do it by hand. K. Now, M can be obtained. Don't think I need this anymore. M can be obtained from a particular diagonal coefficient of the Kirchhoff polynomial. Bad board usage. Okay. Can be obtained as follows. So here we need V to be a vertex with no loops on it. And then what are we going to do? Well, I want to take the diagonal coefficient. I'll write out what it is in a moment in this. So here I do have the minus V, notice, even though my Martin is on K itself. So I take it to the power KR. And in here, I have A1 to the K minus 1R all the way down to A, K, N minus 2. N is the number of vertices, K minus 1R. And so R can be really anything. This then also satisfies star. And that just means it's just going to be off by some normalization, because it only differs from Martin by the base case, right? So only differs from M by the base case, by a normalization. OK, do I want to write down the actual normalization? OK, fine, I'll write down the actual normalization. What is the normalization? OK, it turns out you need an R factorial to the K n minus 2. Then you have this thing. I don't want to write it again. It goes in here. Then that equals KR factorial, Martin of K. Oh yeah, I knew there was a reason I wanted to write this, because I need a little bit of notation. What does this mean? This means I'm going to replace each edge of G by an R-fold multiple edge, which we were calling R duplicating. OK? You R duplicate each edge. OK. So that's nice. But it turns out C2 is also can be obtained from a diagonal coefficient. Also be obtained from a diagonal. From such a diagonal. So in particular, OK, I'm going to write it out. Minus 3p squared C2 of P of G is equal to this thing, A1 to the R. There's no K. The K is not as exciting this time, because the K is 2. Yeah, OK, sorry, n minus 2 R, 2R G, mod P cubed. And here R is P minus 1. And OK, you're like, wait, what about P equals 3? Well, I really don't have time to tell you about P equals 3, but something similar but messier happens for P equals 3. Similar but messier for P equals 3. And actually, that's where we started. Because what Simone and I had been doing for the past 3 years, say, is when we'd been looking at the variant of this that shows up in the messier case when P equals 3, which you can also use all of the time, in fact. So you can write down something more complicated that works for all P, or if P is not 3, you can simplify it to get this. And we've been working with that more complicated version that works all the time. But we didn't have this Martin to compare it to. So we knew, well, not exactly this, but something very similar. But look, C2 of G is equal to this coefficient. This coefficient, K minus V is G, is equal to Martin of K, or some duplication of K. So you're done. Completion is done. The Martin is at the completed level. And that actually, so you're done. There's nothing else to say about completion once you've proved that these things really are diagonals. That gives C2 completion. Because you've said that C2 of G is related via some annoying normalizations to Martin of K. So completion is completely done. The only part that's actually difficult to prove is this part. You need to know that this satisfies star. All right, and I'm going to, in -1 minute, tell you the key idea of that, because it's actually cute. So the only thing to prove, I mean, there's always details. You have to prove all of it, of course. But the only thing that you really need to prove that's interesting is this part, this. It's super cute. Because what do you really want? Well, what is this coefficient really saying? It's saying I do this R duplication of the edges. Okay, but what are the terms in here? These are the complements of spanning trees. Okay, I just flip everything around. So let's just say they're spanning trees now. So I'm looking here. I'm trying to find k-1 are copies of each edge. So I'm trying to find some constant number of copies of each of the edge in a graph here like this, where I've duplicated each edge r times. But all of those things that I find, all those bits and pieces, have to be spanning trees. So I'm really just asking, how many ways can you decompose this graph into a disjoint union of spanning trees? That's the story. Hey, people have studied that before. Okay, and then what do I really want to do? I want to show that it satisfies this recurrence. So I got some particular vertex that I care about. I've broken this up into a bunch of spanning trees. So I got all my spanning trees here. And I want to get rid of this vertex and replace it with a matching. So I've got the components that would be left over if I remove that vertex. And now I need to match them up into a tree. Okay, well, if I want to connect these things together in a tree and keep the information of where they were connected, I know how to do that. And sometimes you might teach it in a second-year course or something. Actually, I don't know if it's in any second-year courses here, but I have taught it in the past. It's just a proof for encoding. So the only thing to prove is that. And how you do it by an explicit bijection using the proof for code. It's kind of cool. I always like it when things you teach in your lower division courses actually show up in a research problem. So that's pretty cool. That's the part Erik and I actually did on the board when I visited him in Oxford. And then the rest of it was just details. So I'm sorry I didn't tell you how it comes from the Martin polynomial, but if you know what the Martin polynomial is, if you take a derivative in appropriate variables and pull out a coefficient, then that's your Martin invariant. That's why it's called Martin. Okay, and I'm going to stop there because I'm already over time. Thank you very much for listening.
Thank you for the talk. Are there any questions? Yeah, I guess okay. Sorry, let me just say that.
Sorry. May I just ask this, how to read this 5GP square thing? You say if it's a polynomial in P, then it implies that the formula that you erased, this PG, this integral, is a zeta function. Is that a clear thing? Like all
no,
C3?
It's not a clear thing. That's the part that goes through the motives. And so I would not even say all of that is a fully rigorous thing, but it's part of this sort of yoga of motives that that community has.
And no further questions. Let us thank again.